What's up, scholars? Today we're going to be doing a little experiment with friction. We're going to be using actually the cart that you've seen a little bit in class. These things are really cool. They hook up to devices using Bluetooth, and they have a bunch of sensors. So not only can they track position, they have accelerometers that can track acceleration in X, Y, and Z. The coolest thing that they have for what we're about to try, which is to talk about friction, is up front here there is a little force sensor. So the way that this works is there is a little tiny spring inside. It's hooked up to an electric sensor, and basically when you push on it, I've got one here, when you push on that front there, it will register how much force you're applying in newtons, which is really great. So we're going to be using that to learn a little bit about friction. So we're going to kind of do a standard experiment when it comes to doing friction, and I'm actually just going to show you what that looks like here. So I've got my force sensor. I've got two books with a laptop stacked on top of it. This is something like 6 kilograms or about 13 pounds or so. About 14 pounds. Anyway, what we're going to do is we're going to push it, and what we're going to do is we're going to see how the force varies both while we're pushing it and once it starts moving. So check it out. Okay, so what we saw there was it wasn't moving at first. That was during this section of me pushing. So I was pushing and it was pushing back harder and harder and harder until I got to this peak here, and then it started moving. So this region over here is the static friction region. It starts to move when I reach the maximum amount of static friction that the book and table interface that friction can supply. And then once I start pushing at a constant speed, this flat part here, that is how much kinetic friction or sliding friction the table can provide. So I did this experiment again, but I took away one of the books. That's a reduction of about 2.4 kilograms. We'll see what happens when we do that. So we're going to repeat the experiment. You can see I've removed one of the books. Check it out. Actually, before I start in this video, make a prediction. What do you think is going to be the difference? Make it that prediction, maybe even write it down in your notes before we get started. What do you think the curve is going to look like? Is it going to be spikier? Is it going to be shorter? What's the difference going to be? Make that prediction now. Okay, let's check it out. Okay, so you can see it's a little blurry there, but you can see that it's almost exactly the same shape, except for now because there's less mass and less force pushing down on the table. This means there's less friction. So the peak force that the table book interface can supply is smaller. There's less friction available. You've had this experience before. It's much easier to push things that are lighter. You'd much rather help your friend move a light couch against a heavy couch. You can also see that the kinetic friction region looks very similar. It's nice and flat as I pushed it at a constant rate. So let's actually take a closer look at that data. This is what it looked like in graphical analysis. You could see I was recording there. For some reason it changed colors, but it's the exact same data. So what we're seeing here in red, those are the two books with the laptop. That's 6 kilograms. And the blue one here is the one book with 3.6 kilograms. So again, maybe it's not that surprising. The amount of frictional force available at this peak is smaller for our lighter object when we were just pushing one book with the laptop. So let's actually look at the two pieces of data we're going to need for each of these experiments. So the first one, we look at the peak there. We're going to need that in a bit. It's about 19 newtons of force to push a 14-pound or 6 kilogram book. And the average force during this flat part, the kinetic friction, is about 13.5 newtons. We're going to need both those pieces of information. And if we look at the other one, same scale and everything, so you can see it's smaller. Our peak, instead of being about 18.5 or 19 newtons, is about 12.5 newtons. And then here, this mean, instead of being, Instead of being 13.5, it's only about 8.5. So in general, everything's easier to move and easier to keep moving when you've lightened your load here. Alright, scholars, we're going to take some notes on friction on a flat surface. So if you don't have it yet, take out your notes. So we're going to just draw the scenario that we just showed. I'm going to simplify it just a little bit to a person pushing a box across the floor. So go ahead and draw this along with me. I'm going to draw a very interesting looking squatting person. They're pushing a box. They're going to try to push it across the floor. Right now, we're going to just talk about static friction. So this is zero velocity, zero acceleration. It's not moving yet. We're just applying effort. And what we just saw in our set of data is that the way this will work is your applied force, we'll call that FA, and we'll just plot that against time for right now. It looks like this. You apply effort to the box, and it pushes back. Newton's third law says it'll push back. And the interesting thing about friction is that it will match you, the way we like to say it is pound for pound, like you might hear someone talk about like with boxing or something like that. So what we mean is as you apply a force, it applies a force back. Okay? And then at a certain point, you exceed the amount of static friction the box can push back on you with, and we drop into the kinetic friction realm. And then we kind of go like this for a little while. So let's label those sections. This is the, right here, this is the static friction area. This is the maximum amount of static friction available. And then this region here is, of course, you can call that the kinetic friction region, or sliding or dynamic friction. You can call it really whichever one of those you'd like. So what we're going to do is talk about static friction and show how you can actually calculate what's called the coefficient of friction, basically the roughness between the surfaces. So scholars, I just wrote down this explanation, and I've moved, of course. Let me read it to you, and I'd like you to pause and write this down. So when we're talking about static friction, that static friction force opposes motion, and it's able to match the applied force, FA, we labeled up there, pound for pound. We saw that during the static friction region, until the maximum amount of force possible by friction is reached. So that's right here at the peak. Then the object starts to move, which you saw in the video. How much friction the object can apply to resist its motion. So we push on the book, it tries to resist by applying friction. Depends on the interaction between the surfaces. We talked a little bit before about the van der Waals forces that exist on a subatomic level. So go ahead, write that down, and then we're going to get into the equation for how we actually work with friction. Okay, so this is the equation for friction, which I modified from the equation sheet just a little bit. This is going to be easier for us to work with. So this says that the force of friction, here we're talking just about static, force of friction is less than or equal to this thing over here. This thing over here is the maximum amount of static friction that can be applied. Okay, and that depends on two factors. So that was the force of friction. This is our, what we call our coefficient of static friction. It is a funny little Greek symbol, so I'll put that over here off to the side. So mu, the Greek letter mu, it's written like a scripty U. Maybe practice writing that a few times. So yeah, in the margin of your notebook or wherever, let's practice writing mu a few times. To be clear, it's not an M. It is not that. Okay, you're going to get really confused. It has this long leg up front and this little tail at the end. So make sure you're comfortable writing the Greek letter. That's the Greek letter mu. Okay, and remember that stands for coefficient, in this case of static friction. That's what the little s means. So it's a Greek letter mu. Okay, this is a unitless quantity, unitless, and it's between 0 and 1. Okay, it's essentially the roughness between materials, and it depends on those two materials. So for example, if you have rubber tires on the road, on a dry road compared to a wet road, the coefficient of static friction is going to be different. 1 is grippier, 0 would be essentially no friction. Because if you make this 0, then there is no ability to have friction at all. And then finally, in the anatomy of our little equation here, this is just the normal force. Okay? It's really important that we understand that the normal force is how hard the surface is pushing up. Once we put a block like this on an incline, it makes it a little bit more challenging, but that's the important thing to know. This is the amount of force pushing up on the table. So what we're going to do next is, or on the ground or whatever. So what we're going to do next is we're going to draw a free body diagram for a box that is not moving. What I'm going to do is I'm going to draw it, but I'm going to pause. I want you right now to see if you can draw the free body diagram for box being pushed, not moving. Okay, see if you can draw that free body diagram. Okay, so we obviously start with a dot when we're doing free body diagrams, and we'll add the two maybe obvious forces, the weight or force due to gravity, and then we have the normal force pushing up from the table. Now you're applying an applied force, and the friction force, which I'm going to try, I made that a little bit too long. Okay, so I fixed the length there. This is the friction, the force of static friction, we'll call it. So we'll call that Fs. Okay, or FF, I guess, will be consistent with our equation up here, FF. So that's the force of friction pushing backwards. Importantly, there's no acceleration in the x or in the y direction. Now the next thing we need to do is set up Newton's second law. Luckily we've got our free body diagram. It makes doing that very easy. So let's do that. For the x direction, you've got the applied force and you've got the frictional force. So this side will be F net, that equals ma in the x direction. The net force is the applied force minus the friction force in the x direction, so Fa minus Ff. And that's going to equal ma in the x direction, but that's of course 0. So that makes this whole side 0. If we add Ff to that side, we get the applied force is equal, to Ff. So the amount of force you're applying is equal to the frictional force. That makes perfect sense because we're not moving. Then let's do it in the y direction, so up and down. And of course we're pushing across a flat surface, so there is no acceleration in that direction either. Ma in the y direction. So our net force here would be the normal force pushing up, the weight force pushing down, so Fn minus mg, that equals ma in the y. Remember, ma in the y is 0 again. So that whole side is 0, which means we can add mg to both sides, and we get the normal force equals the weight force, which again isn't maybe that surprising. You have the box pushing down, the normal force pushing up. What we want to do now is figure out how we can determine, for example, something like, what is mu here? What is the coefficient of static friction? And the way that we can do that is that we can substitute in what the frictional force is. Because we're at the peak here, we can actually just ignore that less than or equal to, because this is the moment when we've reached the maximum amount of frictional force. So what we're going to do is, instead of Ff, we're going to write mu normal force. So Fa, the applied force, is equal to, I'm going to put that in parentheses since we're substituting, mu s times the normal force. Okay? Oop, you missed all that. So all I did was, where I saw Ff, the frictional force, I substituted in mu times the normal force, the coefficient of friction times the normal force. Now, one more step, and we've got our equation that we can work with so that we can go do our calculation. We're going to try to calculate mu. We know in this case the normal force is equal to just mg. So we'll substitute mg right here into normal force, and we end up with the applied force, the amount of force I applied, which would be this peak here, that's equal to mu s, which we don't know, times the normal force, which is just, in this case, mg, and we do know that information. Okay? So what we're going to do next is we're going to try to solve for mu s. The way to do that is we just solve that. So mu s will be, I can section this off a little bit. Okay, so mu s will be Fa divided by mg, the applied force divided by the weight force, and we actually have all of this information. So if we go back to this one here, for our first example, we know that the mass is 6 kilograms. The peak force there, the applied force, is 18.68 newtons. Take this data and see if you can calculate mu for our static friction. So if we take from our graph from a moment ago, 18.68 newtons, We plug in 6.0 kilograms, multiply it by g, which is 9.8 meters per second. We have we get 0.32, and you can convince yourself that it is indeed unitless. Newtons is kilograms meters per second squared, if you just look back at Newton's second law. And on the bottom, we also have kilograms meters per second squared. So when we do that division, we end up with a number like we predicted between 0 and 1. Okay, so I want to pause here and just look at what we've got. A couple of things. First of all, what does this mu s mean? Well, what this means is, like, let's just say, for example, the coefficient of friction mu s was exactly equal to 1. What that would mean is that the force you have to apply is exactly equal to the weight. But it's not. This moderates how hard you have to push by about 32%. So if the thing weighs 100 kilograms, or has a mass of 100 kilograms, let's say, then you only have to push with about 32 kilograms, whatever that translates to in force. So I want to jot down, I'll pause and jot this down, but I want to give you sort of in a plain English sense what this equation means. And I also want to point out that so we'll put this in a box, this is going to be useful, but it's useful in an extremely limited context. This is only valid on a flat surface. Okay? Of course, being AP, we have to make things difficult. We're going to end up putting things with friction on an incline. So let me write down in plain English what this means, and then we're going to move on to kinetic friction. All right, so that last note there, it just squeezes it into the corner. What this equation that I've boxed in red is saying is that the force of friction, or the applied force here, they're exactly equal at this moment, but the force of friction here is proportional to the weight and surface roughness. So mu is the surface roughness, and mg is the weight. Again, that's only valid on flat surfaces, but that's what this is saying in plain English. Okay, so now that we've handled the static friction, let's talk about kinetic friction. And so we're going to continue on to the next page here. Same title, friction on a flat surface. I've recreated my beautiful drawing, but now the person has it moving at a constant rate. So we're not accelerating, but we are moving forward, which means all of our forces are balanced. How hard we're pushing, and we can measure that with the force sensor, is going to be equal to the frictional force pushing back against us. So what we're going to do is we're going to set this up in exactly the same way. The equation is going to be the same, but now we're going to find the kinetic coefficient of friction. So whereas the static friction, so I'll just write recall, mu s, so the static friction was 0.32, we want to find the kinetic friction. So I'm going to try to walk you through how to do that in a relatively swift manner. So here we have our equation. I've very slightly modified it. I've taken away the inequality because we're pushing at a constant rate. So the force of friction being pushed backwards is exactly equal to the kinetic friction coefficient times the normal force. So what we'll do is we'll set up the free body diagram, then we'll do Newton's second law. Take your best guess at drawing the free body diagram. Go ahead. So there's a free body diagram. It looks remarkably similar, in fact, identical to the static friction one. The reason for that is we're not accelerating. We're moving at a constant rate. So you've got your applied force, you've got the kinetic friction force pushing back, you've got weight and normal, respectively. Now, I'm going to walk you quickly through how we do the second law here. It's the same deal. We're going to need to do that in the x and in the y. So once again, in the x direction, we have F net equals ma in the x. It's going to be remarkably similar to what we just did. The x acceleration is equal to 0. So we have Fa minus Ff, that's the net force in the x direction. That equals 0. So again, the applied force is exactly equal to the frictional force. And then in the y direction, we have F net equals ma in the y. That's, again, 0. We're not moving up and down. So we have the normal force, which is up, minus the weight force, which is down, and that equals 0. So the normal force, again, is equal to the weight force. Not always true, but true again in this specific case. Let's then substitute in the frictional force. This is the same procedure that we just did. The applied force, remember, we're measuring with our force sensor. We saw that in the video. So Fa equals F, the force of friction. That's just mu k times the normal force. We just showed that the normal force is, again, the weight force. So Fa equals the coefficient of kinetic friction times mg. Okay, again, this looks remarkably similar. I'll put them side by side. So this is for the kinetic case. This is for the static case. They look identical. This, again, is only valid for a flat situation. Let's take a moment and calculate mu k. So again, of course, you can see that mu k, just solving by dividing by mg on both sides, is going to be equal to the applied force divided by the weight force. What I'd like to do, so let's take a look at the data. We don't care now about the maximum force. Instead, we care about sort of this average force during the flat part of the graph. Here's what that looked like without the data in front. So it's kind of flat and nice here. The reason it's not perfectly flat is because the surface isn't perfectly smooth, and I'm probably applying a varying amount of force because I'm a human being. So if we go back, we can see that the force we're going to plug in is 13.5. We'll just round it or truncate it there at 13.5. And we're going to use the weight force, which is the same as before. So mu k equals 13.5 newtons over 6.0 kilograms. Again, this is the same object that we were just talking about. And we'll do that times 9.8 meters per second squared. And before we actually type it out, let's make a prediction. Since there's less force being applied by the kinetic friction, what we should expect is for this to be a smaller number. Our numerator has gotten smaller, so let's check that out. So when we punch everything in, we get that the kinetic coefficient of friction, the coefficient of kinetic friction, is 0.23, which is less than what we got when we had static. So we can compare those. So this was our answer here. For static, it was 0.32, which is exactly what we expected. Okay. Now, in general, this is true. So in general, the coefficient of static friction, which is less than 1, remember it's going to be somewhere between 0 and 1, is going to be bigger. The alligator eats the bigger thing, bigger than the kinetic friction, and all of those are going to be, in general, bigger than 0. So this is generally true, and that is your quick summary of friction. Okay, the last thing I'd like you all to try is to do what I've written here. So you're going to use the trial with one book and the laptop, which I'll include the data on Google Classroom. It's 3.6 kilograms, and you're going to use it to calculate mu s and mu k. So the reason I want you to do this is so that you can get a chance to practice, and also it's very possible they won't be different. So what I want you to do is compare it to the two numbers. Is the coefficient of kinetic and static the same? We have the same book, the same table, the same interaction between surfaces. Do we actually get the same answer? So you're going to use this data. You'll need this peak force and this average force to make that calculation. And along with posting your notes in Google Classroom, I'd also like you to answer the question, do they come out the same? Compare mu k and mu s for this case, the one that's on the screen right now, to the one that we just did as an example, which was this case here. Good luck. Let me know if you have any questions.